Welcome back to the channel. In today's lesson, we'll see capacitors in series and parallel. In our previous lesson, we saw resistors in series and parallel. In case you missed those lessons, please do not hesitate to check the description below. I will place links to those lessons in the description below. That said, let's get into class. When capacitors are connected in series, current emanates from this voltage source, and if we call this current I, it obviously will deposit charge across each of these capacitors, and the charge deposited on these capacitors will be uniformly deposited because the capacitors are connected in series, so that equal charge will be deposited. But for the total voltage across the set will be equals to the sum of their individual voltages, so that V is equals to V1 plus V2 plus V3. Remember we said that charge Q is equals to CV. So that if we are saying charge Q is equals to CV, this implies that my voltage V is the same thing as Q over C. Now, so that to calculate the effective capacitance across the circuit, my Q now over the total capacitance will now be the same thing as my Q. Remember we said equal charge will be deposited, Q over C1 plus Q over C2 plus Q over C3. Now I can now come out with Q, here is CT, will be equals to 1 over C1 plus 1 over C2 plus 1 over C3. Then I'll bring out Q. So I can now divide Q by both sides. Then I'll be left with 1 over CT to be equals to 1 over C1 plus 1 over C2 plus 1 over C3. Now let's see it when they are connected in parallel. Now when capacitors are connected in parallel, it will also deliver current I. And on getting to this point, on getting to the node here, it will now move. The current will actually be divided into the loops, so that the charge deposited on C1 will be different from what is deposited on C2, will be different from what is deposited on C3. But for the voltage, just like we saw in resistors in parallel, the voltage across the capacitance would actually be the same thing. So if the charge is going to be different, we're saying that the total charge QT will be equals to Q1 plus Q2 plus Q3. Now we said that the charge Q will be the same thing as CV, so that C total times V will be the same thing as C1 times V plus C2V plus C3V. So that C total now times V will be the same thing as C1 plus C2 plus C3 into V. Now we can divide both sides by V like we did the other time. So that CT for capacitors in parallel will be the same thing as C1 plus C2 plus C3. Now, so that as a rule of thumb, when capacitors are connected in parallel, we simply add the individual capacitance. But when capacitors are connected in series, we take the inverse of the capacitance. Now, let's take an example that will help us understand it better. Our question says, for the arrangement shown below, find A, the equivalent capacitance of the circuit, voltage across the 15 microfarad, and the charge on each capacitor. Let's see it this way. Let's start this way. First, we have to find the equivalent capacitance of the circuit. That is, if you look at the circuit, you see that we have two capacitors in parallel, and the whole combination of the parallel capacitor is now in series with the 15 microfarad. So that the effective capacitance now will come from, you have 2 microfarad in parallel with 3 microfarad, and this combination is now in series with the 15 microfarad. So that for the parallel combination, let me refer to the parallel combination as 1, that is as my C1. That will be equals to 2 plus 3, which is equals to 5. 5 microfarads. 1 over Ct, so that 1 over Ct will now come from 1 over 5 plus 1 over 15. 1 over Ct will now equals to, here is 15. 5 in 15 is 3. 3 times 1 is 3 plus 15 times 15 in 15 is 1 times 1. Now this is equals to 4 over 15. And Ct obviously will take an inverse of both sides, become 15 over 4 microfarad, which is something as 3.75 microfarad. First, let's redraw this circuit. Here's the original circuit. Now, if you look at this circuit carefully, we are to look for the voltage across the 15, and the total voltage across this circuit is 240. Now look at it this way. We have broken this circuit down into, break it down into two series circuits. Yes, 240. So we can, in place of the parallel combination, replace this parallel combination with this, so that I have 5 here. This is the 5 microfarad, and this is 15 microfarad. We're interested in the voltage across 15 microfarad. Let's call this VB, and let's call this VA. Now, if you look at this circuit carefully, you'll see that we can now use a ratio of the two circuits, because obviously I have 240 volts here. Obviously, my 5 of my VA will equals to 15 of my VB. We're taking a ratio of both sides. So that if 5 of my VA will be equals to 15 of my VB, obviously VA will be equals to 3 VB. And we know that my VA plus VB, both of them sums up together, because it's a series circuit, into 240 volts. So that in place of VA, I can have 3 VB now to equals, I can have 3 VB plus VB to equals 240 volts. So that 4 VB now equals 4 VB equals 240 volts. So that effectively VB, which is the voltage across the 15 microfarad, will be the same thing as 240 over 4, which is equals to 60 volts. Now, if VB is 60 volts, VA also will definitely be, which is equals to 3 VB, will be the same thing as 3 times 60. So that VA will be the same thing as 180 volts. We have gotten VB and VA. Now we are left to find the charge on each capacitor. Now let's find the charge on VB first, because we got voltage for VB first. Now the charge on, as the charge on 15 will come from Q is equals to CV. So that will be Q now on the 15 microfarad will be equals to 15 times 10 raised to power minus 6, that's 15 microfarad, times the voltage of 60 volts, which is the same thing as, from my calculator, 15 times 60, that's equals to 900 times 10 raised to power minus 6 coulombs. So we can easily write that as 900 coulombs. Now let's look for the charge across the 2 microfarad and the 3 microfarad. Now for the 2 microfarad that's the voltage across the 2 microfarad is 180 volts. The voltage across the 15 we reduced it to be 60 volts. So that across the 2, for the 2 microfarad, we're saying that Q will be equals to 2 times 10 raised to power minus 6 times 180. That will be equals to 360 times 10 raised to power minus 6. So that Q will be equals to 360 microcoulombs. Now, across the 3 microfarad, we're saying that Q across the 3 microfarad, we're saying that Q is equals to 3 times 10 raised to power minus 6 times 180, which will be the same thing as 540 times 10 raised to power minus 6. So that Q will be the same thing as 540 microcoulombs. And with this, I hope you understand how to work with capacitors in series and in parallel. In our next lesson, we'll take more examples on capacitors in series and in parallel. Thank you for staying with us, and do not forget to subscribe to our channel if you have not subscribed. Thank you, and see you in our next class.